calcium excess calcium that's left in the cytoplasm can be mopped up by another calcium securing protein called calmodulin. So named because it modulates calcium ion activity. Really, calmodulin is, again, everywhere. This is not just a protein that is unique to muscle cells. It's inside neurons. And as we'll see, neurons also use calcium as a messenger molecule. And in neurons, it's perhaps even more important that they're very precise in how they use their calcium. And this calmodulin is there to, well, any calcium that didn't get pulled back to where it belongs by a calcium pump can be bound up in calmodulin and kept from doing anything unintended. That is by no means a complete thing, and you have to think about calmodulin as this protein that when the muscle cell is completely at rest, binds up these extraneous calcium ions. In moments of real activity, you're actually using the muscle, and you're running or lifting weights or what have you, there's so much calcium out there that obviously calmodulin can't bind at all. That would be bad, because then the calcium couldn't go out there and bind to the tronin. So this is purely a mop-up. It's kind of, think of it as the cell being kind of obsessive compulsive about its calcium. And we can't just have those calcium ions flying around out there, accidentally initiating excitation contraction coupling. So that's the end of those slides. We're going to move on to skeletal muscle dynamics are the next slides. Any questions on that stuff?
Could you hold on just a second while I finish writing?
Well, sure. I'll have a little more coffee, which will then allow me to speak even faster, and then I'll have to stop again later. But, what are you going to do? I once stipulated that I needed to stop having coffee before class because I ended up speaking too fast.
I got it. Thanks.
Let's just say I've fallen off the wagon. Stop share. Now I'm going to reshare to something else. Go away. There we go. Share screen. Let's see. Could you repeat what happens when there's too much calcium ion? Well, but if by too much, if you had really too much calcium ions in there that overwhelmed everything, your muscles would go into a constant contraction and you would never be able to relax. That's not exactly what the calmodulin is about. Although I suppose you could argue that maybe one of the original selective advantages for having calmodulin in there would be to prevent those kinds of contractions in muscle, which tend to be not useful. I mean, have you ever found any use for a muscle cramp? No. But the calmodulin out there it's a kind of calcium buffer. You can imagine a muscle getting into a real excitable time where it's working very, very hard, and the calcium is cycling back and forth and back and forth and back and forth in and out of the sarcoplasmic reticulum. And put succinctly, if all of the calcium that was stored in the sarcoplasmic reticulum were to somehow be out at the same time in the cell, and this is a little unclear exactly what happened, but certainly the potential there is that all that calcium might cause actin and myosin interactions that are too severe and unwilling to stop interacting. So you have this calcium buffer out there that dampens any real spikes in calcium concentration that might result from over release of calcium out of this SR. So what's the final product here? The final product of these sarcomeres contracting in series and creating a very large length change is we're going to do work, and we're going to do work at some rate. Obviously, if you look at it at a molecular level, the myosin heads are grabbing actin, and they are accelerating that actin toward the middle of the sarcomere. So that's a force being applied. The mass is being accelerated, and those Z discs are accelerating toward the middle. Now, that's within the cell. If you then step back and look at what that cell is actually moving, you start to add the mass of, oh, I'm pulling on the tendon, and now I'm pulling on the bone, and that mass, and now I'm pulling on the weight that I'm lifting, the actual point of purpose. But at some level, there's always going to be some mass being accelerated. There's going to be some force produced. Now, the distance over which that force is applied, as you'll recall, is the work being done. So if you thought about the sarcomere shortening, it's being accelerated toward the middle with some force, and it's going to be applied over some distance, and that's going to be the work that the sarcomere has done. You add all of that work together in a series, and you've got the work that an individual muscle cell does, and an individual muscle, and so on. Now, you've probably noticed that if you do things slowly versus do them fast, you are less likely to be fatigued. That's because the amount of work you do divided by time is power. Power is this, is what, keeping up with the cellular demands for power is what your cardiovascular system is built to do. And that is, it has to provision these cells with, at a certain rate of work. That means they have to be provisioned with fuel and oxygen to burn that fuel. And so we tend to be preoccupied with power when it comes to the whole metabolism of the animal, because we're very aware of our heart beating, and we're very aware of our breathing. And as it turns out, those are directly correlated with how fast we're running. So, or how fast the bird is flying, how fast the animal is swimming. So power is certainly important to us, especially when it comes to locomotion. But it's not always the physical parameter that matters. If you need to just stay in one place, or say I need to lift my coffee cup, the speed with which I bring it to my lips really doesn't matter. I mean, there's a few critical moments in the morning that it might matter. I really got to get it there. But mostly what matters is that I can produce adequate force to hold the coffee cup up, right? That's just pure force. Yeah, and you really do need to be able to do the work to bring it from here up to here. That's work being done. But again, the rate is kind of irrelevant. It's going to get there. But when it comes to locomotion, frequently what we need to do, especially if we're being chased by a lion, is we need to do that work in a certain minimum amount of time, which means high power. Otherwise, we're not going to make babies. So it depends what you're doing. If all you need to do is be able to hold on to the tree branch, you've gotten away from the lion, you've climbed the tree, and now you're just hanging by your by your grip in terms of the sarcomeres themselves in your flexors of your hand, the only thing that matters is how much force can they produce. So sometimes that's what matters. I need to hang on, need to hang on, need to hang on. Now, whole body though, your whole body power in terms of your cardiovascular system, breathing still needs to produce high power because it has to provision at some rate. Your heart has to provision at some rate the fuel necessary to maintain that force. So you need to think carefully about, you know, what are the physics of the system at this moment? What's meaningful? Sometimes it's work, sometimes it's power, sometimes it's force. That clenching of the tree branch where you are producing force, but you're not moving. That is, you know, you've got the tree branch and you're hanging onto it. There is force being produced in your flexor here in your forearm, but there's no sarcomere shortening. You've shortened all you can, you're just gripping. That's an isometric contraction. Versus isotonic contractions are one where the muscle produces force and then also shortens. Or, that's in this case of a concentric contraction, you also have the occasions where muscle force is being produced, but instead of shortening, it actually lengthens. Now, that may seem like a peculiar instance, but if you've ever lifted weights and you're doing the bench press and you're pushing the weight up, you know that when you bring the bar back down, you must be producing force. Otherwise, the bar would fall toward you at 1G and you would be crushed. And so you're producing force on the way down. It's slightly less force than the force of the mass times the gravity of the weights. But your sarcomeres are still producing force, yet they're lengthening, they're stretching at the same time. So that's kind of a poser when you start thinking about our little myosin heads going ratchet, 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 and moving our sarcomeres. How in the hell do they produce force when they're lengthening? Good question. Turns out nobody knows, but they do. It could be something. Yeah.
Can you explain isometric contraction again?
Isometric is simply when your muscle is producing force. That is, the myosin heads are binding to actin, and they're bound to actin, and they're trying, if you will, to move the sarcomere, except they don't. And so an isometric contraction is simply when, so let's just say I'm sitting here with my bicep and I'm holding up my coffee cup. That's doing an isometric contraction right now. My bicep is just equaling the force of the coffee cup plus my arm. And it's contracting, it's producing a force, but it's not shortening. In other words, no work is being done. Turns out I don't care about work. All I care about right now is holding the coffee cup up. It has to just produce force. Okay? That's isometric.
Thank you.
There's a whole bunch of exercises out there, and they're horrible. Horrible. They're very effective. They're horrible, though. Don't do them. They call isometric exercises where, you know, you're just holding your, well, yoga in general is one exercise after another in isometric contractions. And there's a reason I don't do yoga. It's torture. Horrible thing. Anybody do the Bikram's yoga where it's like 500 degrees inside the room or something?
Me, I love it.
You love it?
I do.
Well,
it's so fun.
It sounds horrible.
I can't wait for COVID to be over so I can go back.
Oh yeah, but you haven't been able to do that because, as I understand it, it gets quite sweaty and I can't imagine it smells very good either. I mean, God. Well, you don't. But there aren't any guys in it, right? Are there any guys in this class?
Yeah, actually, but they're all kind of older.
Yeah. I think I understand that. I'm surprised. I would keel over. There's no way. Anyway, those are right. Most of those yoga poses are, are isometric contractions. You're recruiting muscles. You're holding yourself, your own body mass against gravity, but you're not actually moving much. So everybody okay with concentric and eccentric, or eccentric as it's sometimes called?
Can you just repeat which one is shortening and which one's lengthening?
Concentric is normal. Think eccentric is weird. That's eccentric contraction. It's really not a contraction. It's a lengthening. So it's an eccentricity of the actin and myosin interaction that nobody really understands very well. You can imagine the myosin heads, some of them pulling on the actin and keeping it, grabbing on and keeping it from lengthening. And then others letting go and cycling and cycling. It's just fewer myosin heads grabbing the actin, and they're producing force in the sense that they're acting as brakes to the lengthening of the sarcomere. So they're grabbing on but at a molecular level, exactly how the energy is released and how that works with the myosin heads is kind of a curious and difficult to think about phenomenon. But suffice it to say, it works, which is important, and we'll leave it at that. Remember that every muscle cell or fiber has some kind of neuronal attachment to it. You can't get a skeletal muscle fiber to do anything without a nerve attached to it. And so we call the neuron that is serving the muscle cell and the muscle cell itself a motor unit. Thinking about this, you have to remember that every muscle cell needs a neuron, but you don't necessarily need, every muscle fiber doesn't need its own neuron. Let's put it that way. So in other words, let me just illustrate. So you've got muscle cell here. And in theory, you could have a whole neuron. So the neuron, the cell body is up here, and it's sending out an axon, and it's talking to this muscle cell all by itself. You could do that. Turns out, I don't know of any instances in a vertebrate body where that's actually the case, where a single muscle cell has its own single whole neuron to serve it. What instead is going on all the time, as far as I know, as far as anyone knows, is that you're going to have a bunch of muscle cells, and you'll have a neuron that comes down and it splits. Say in this case, not like that. Sorry, I made a little octopus or a cnidarian. It splits like that and has branches of its axon that will attach to each muscle cell. So in that way, we have adequate representation. That is, we have the needed excitation of each muscle cell. But that also means that for this one neuron, when it fires, that is, it tells something to go, it's going to have to tell a minimum of 3 muscle cells to go at the same time. That would be a motor unit right there. That neuron and the 3 muscle cells that it serves. Turns out, and so that's innervation ratio. You've got 1 neuron for 3 muscle fibers. Turns out that's a really, really high ratio. In fact, more typical innervation ratios, I think the smallest one in a human body is 1 to 10. And those would be the muscle fibers in your eye that move your eyeball around in its socket. Obviously, skeletal muscle fibers are skeletal muscle fibers. To a certain extent, they're going to all produce about the same amount of force. There's a little variation. We'll talk about it in a second. But obviously, moving your eyeball around in its socket does not require a lot of force. If it does, you have problems. You probably have gravel in there. You probably need to use some lubricant. So because it doesn't require much force, when a single neuron says, go, go, gadget, eyeball moving, and it wants to move your eyeballs to the left, you don't want 10,000 muscle fibers going, yeah, and yanking on your eyeball over to the left and and yeah. Oh, I sprained my eyeball. Now, you want small forces, so you recruit few muscle fibers. And when you recruit only 10, you get small forces. Understand that because that is the smallest recruitment, that is the smallest ratio of or the biggest, smallest ratio of muscle fibers that you can recruit, 1 to 10, that's the kind of it sets a minimum to the amount of force that the muscle can actually produce. Contrast that with, here, let me erase this, clear all drawings. Contrast that with the innervation ratio. So here's a much better picture of innervation ratio. Here you have 1, 2, 3, 4, 5 muscle fibers all being spoken to by, oh no, sorry, here's 3. And then here's another neuron talking to two. And again, it's drawn this way just because it's difficult to illustrate real innervation ratios of 1 to 10, or what is much more typical, 1 to 1,000 or 10,000. Now, the reasons for that are fairly simple. There's no reason, you'll rarely be required to produce forces below some minimum. Even your eyeball movement, 10 muscle fibers is plenty, but anything less than that is kind of stupid. And you would just have to, if you did it instead 1 to 5, you would have to have 2 neurons to stimulate the same 10 muscle fibers. And neurons are hideously expensive. They take oodles and oodles of ATP. And so having an individual neuron going out to every muscle cell just to turn it on is a waste of ATP. It's a waste of anatomical space. It's probably not physically possible. You have trillions of muscle cells, and trying to serve them all individually with neurons is stupid. That individual, were there a mutation, would not make many babies. They would be a giant bundle of nerves, literally. So instead, we have innervation ratios. Your gastrocnemius is your calf muscle. It's the very large muscle, one of 2 back there in that part of your leg. And obviously, extrinsic eye muscles, that is, muscles moving eyeballs, very small forces. Your gastrocs, on the other hand, you say the C when you just shorten it to gastroc. Your gastrocs, your calf muscles, on the other hand, are tasked with full body weight support. So here they are doing their thing, and at any given moment, the forces, the minimum force they would need to produce is always quite large. So why not have 1 neuron turn on 5,000 muscle fibers? Might as well. You're always going to need at least 5,000, so what the hell? These innervation ratios then are tuned to the locomotor and biomechanical needs of the individual. They're tuned for best efficacy, that is, I need this amount of force always, so please turn on lots. They're tuned for efficiency. I don't need to waste neurons doing this. So imagine when they are tasked with something other than what they normally do. For example, there are some great examples, some painful ones. It's fascinating when you think about a lioness, for example, that can throttle a wildebeest or a zebra with its jaws. Incredibly powerful masseter muscles that can produce tons of force and crush anything, the life out of any living thing. And then later, when they have to move their cubs because they have a new lion around, they have to move their den so they keep their cubs from getting killed. And they're picking up their lion cubs, and she's picking up her little lion cubs in that same mouth. And somehow doing it, you're picking them up, and the same jaws that can throttle the wildebeest are now very delicately picking up the cubs and carrying them somewhere else. That's all a matter of how many muscle cells do I turn on in that instant. And for a lioness, you might think that every time she closes her jaws, there would have been selection for efficiency. Just close them all. You're throttling a wildebeest. But obviously, there are occasions when I need to produce less force. Lions, after all, play. And they wrestle around, and not everything they do is a killing blow. And so they have the innervation ratios that allow them to be judicious in their force production. He just died. There was an African elephant down at the wildlife safari place in Winston. I can't remember his name, Ralph, something like that. Is a big, beautiful African elephant, and he just died. He painted, and so for extra dough, you could go get him to paint something for you, and he would take the paintbrush in his trunk, and he would paint. And no, don't get me wrong, the paintbrush was pretty sturdy, and these were not the Mona Lisa when he was done, but it was remarkable how delicate he could be with this incredible mass of skeletal muscle with, one would think, fairly large innervation ratios. But surprisingly, at the ends of their trunk, some of those finer prehensile bits at the end of their trunk were actually clearly had some fairly fine innervation ratios and could do quite delicate things. You've heard the story of them being able to pick up a dime with the tip of their trunk. Yeah, they can actually do that. And here he's holding out the paintbrush, and he's kind of slopping the paint on, and he has probably no idea why we give a damn what he's doing with this paintbrush, but it got him extra peanuts, so he didn't care. Maybe a more tragic story than that is you might have heard of folks born without forelimbs, humans, or lost their forelimbs, and they're forced to do lots of things with their feet and toes. And every once in a while, you'll see them painting or drawing or turning the pages of a book. That is extraordinarily difficult stuff, because the hind limbs of a human with these grotesquely large innervation ratios, if the minimum amount of force you can turn on with your gastrocs, and you're sitting here painting and you're pointing your toe, try this sometime. Can I just touch the camera gently? I'll probably break it. And the answer is, if you're going to try to produce small forces with that, what you're probably going to have to do is at the same time produce antagonistic forces with this muscle up here, such that the net force is small. And so as I'm doing this, I can feel my tibialis anteriors going, no, 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 careful, careful, gastroc, stop it, stop it. And it's really difficult to do. So anybody, if you ever see anybody drawing with their feet and it looks like anything other than what the elephant did, they're doing pretty good. The innervation ratios are all wrong in a human being for that in the hind limbs. Forelimbs, no, we've got it in spades. We very fine innervation ratios in some of these hand muscles in particular. So the key to this is, of course, is recruitment. What we're talking about is how many muscle fibers do we turn on in those cases. As it turns out, it also matters what kind of muscle fiber you're going to turn on. Not all muscle fibers are the same. So what I'm going to do here, and I think I gave this to you in one giant slide. Awesome. The best method is to play in two-player mode where one controller is being controlled by your feet and the other with your hands. Can you pop back a slide? Whoops, that slide? One control being with your feet and the other with your hands. Well, I mean, all the proper flight simulators, you have to run the rudder pedals with your feet. And that's the hardest thing in a helicopter, actually. Helicopters, the muscle inputs, the control inputs are tiny, almost imperceptibly small. And then on top of that, you have to have your feet doing the rudder pedals. And, you know, our legs are built for big forces. And so watching a new helicopter pilot try to figure out how to do things, just dance on the rudder pedals instead of waltz. The first helicopter solo, you'll watch their tails just wagging like this as they try to figure out how much force to apply to those rudder pedals. Not an easy thing to learn. Okay, back. So I'm going to build this table here of different muscle fiber types. And this is by no means all of the muscle fiber types. When you see type, that means that some OCD person has decided they need to have categories. And so they've created these categories. And you'll see all kinds of names for these categories. Especially the exercise physiology textbooks are just full of these things, all kinds of different. There you got the type 1 and the type 2A and the type 2B and the type 7 and the type 9. It's absolutely preposterous. Here's the continuum. There's slow oxidative at one end, there's fast glycolytic at the other end, and somewhere in between is everybody else. And the vast majority of fibers are somewhere in between. Okay? And depending on which end of this continuum they are, you could describe them as type 2 and 3 and 4 and 5 and whatever. I don't care. It's stupid. Don't occupy your brain with stuff like that. Occupy your brain with where approximately on this continuum are they, and does it make sense given what they do? And let's go through a list of characteristics. One of these characteristics is speed, that is the speed of contraction, which ultimately is going to reflect, well, how quickly do the sarcomeres shorten, which ultimately is a product of, well, it's really the force of accelerating the mass of the sarcomeres, right? And when I speak of speed, we're talking about, let's just say it's a muscle that's been taken out, disembodied, and you have it in a petri dish. There's no load on it, there's no nothing. And you turned on that muscle and said, how quickly does it shorten? That's the twitch speed. And the speed of these various fibers varies from slow, and the slow oxidative, hence their name, to very fast glycolytic, hence its name. Most fibers are somewhere in between, intermediate speeds. There are great examples of each at the end of the continuum. We'll see them here in a second. The oxidative versus glycolytic portion is simply reflecting, in the name, is reflecting the metabolic origin of the ATP. Is it derived from oxidative phosphorylation, oxidative, or are the AT a product of glycolytic or anaerobic processes? Some muscle cells, not a lot of mitochondria, are mostly glycolytic. Now, this is a lovely slide. I don't even know where I got it. I did try to do this to it, and I think, did I give you this version of it? Which is a little cleaner. So these are all the actual molecules by, again, some OCD folks that decided, I want to see all of the proteins. No, you really don't. What you want is just blobs. And this is an introduction to one of the modulating forces, that is one of the modulating chemical situations that changes the twitch speed of these muscle fibers. Up here, we have calcium calmodulin. This is calmodulin with a calcium ion. So cam is calmodulin. Here's calcium, and it binds to calmodulin. This is a myosin head, myosin tail, and these are the light chains. The essential light chain, which is just a structural thing, and the regulatory light chain, which is, as the name implies, regulatory. When calcium enters the cytoplasm, it will bind to calmodulin. When it does, calmodulin, this calcium buffer, it can mop up extra calcium ions. As it turns out, when it does that, it also tends to change the activity of this protein, myosin light chain kinase. Myosin light chain kinase then gets turned on by binding to calmodulin with its calcium. That is, calmodulin gets potentiated by calcium. It then turns on myosin light chain kinase, which then causes this regulatory light chain to be phosphorylated by an ATP. So we've added a little inorganic phosphate there to that light chain. Turns out that that regulatory action of the regulatory light chain, when it gets phosphorylated, it potentiates the myosin head. And actually, it's the supercharger. It makes the force that the myosin head produces larger. So for a given power stroke on the myosin head, when this baby is phosphorylated, it's supercharged and can produce more force when it grabs onto the actin and then moves the actin. The ability to do that, that is to produce more force with your myosin head, is ultimately at the root of how fast a cell twitches. A muscle cell can twitch. This potentiation that happens is but one way you can produce more force inside a cell. Oh, we'll talk about others in a minute. By the way, this is something that also gets turned off. There's another enzyme in here, myosin light chain phosphatase, MLCP, which dephosphorylates the myosin regulatory light chain, and you go back to this state. Okay? Myosin light chain kinase, myosin light chain phosphatase, just to give you an idea how important this mechanism is in terms of twitch speed and force production. So here is here's two contractions. Is an isometric contraction and a regular old muscle shortening concentric contraction, and with a muscle cell with moles of phosphate added to regulatory light chains. And so as you increase the moles of phosphate for every light chain, regulatory light chain, these myosin heads are producing, geez, it goes from down here, that's like 40% more force. It's gone up from twitch force of 1.05 to over 1.4 in this concentric contraction. This is a powerful mechanism. You turn on that, with that calcium, that myosin light chain kinase, and you phosphorylate those regulatory light chains, those myosin heads go into overdrive. They really produce a lot more force. So it's an important bit. I'll come back to that in a little bit. Myosin heads, so that's one use of ATP, by the way. That's a different use of ATP, by the way. This is, once you phosphorylate this thing, it stays phosphorylated until myosin light chain phosphatase takes it back. As long as calcium is out here, it will stay phosphorylated. That is a different ATP than the one it takes to cock the myosin head, which is out here. It binds out here, okay? And an ATP is used for every cock and release of the myosin head out there. So this is just one to potentiate it, and it stays potentiated. The myosin head out here is going to have to cycle through a whole basket full of ATP to do its thing. Okay.
Does the phosphate there, does it just like increase the efficiency of the energy use of the other ATP? Like how can it supercharge it if you're still using the same kind of ATP?
That's a good question. It causes a conformational change in how the myosin head is arranged. And presumably that means that when the energy is released in the other conformational change of going from this position to this position, it actually releases it more effectively. In other words, more probably in a quicker fashion or something is what I can imagine. I mean, you're talking about the physics of a molecule moving nanometers here. That's a good question.
But is this process, is this done every time a muscle contraction happens or just in certain cases?
Yes. So this is going to happen whenever calcium is released out into the cell. So as you can imagine, as calcium, so this is a series of contractions. I probably should have explained this a little better. So here's the first one, then another one, and then another one. And notice that the force that the contractions produce goes up. So what you're seeing here is the calcium going out, and it's turning on the myosin light chain kinase. So the longer the calcium is out there, the more myosin heads got potentiated at their regulatory light chain, and the more force every one of them is producing. And so this is an effect that occurs when the muscle gets first turned on and tends to increase. And we'll see the ultimate result of that here in just in a couple of graphs. Myosin heads have an enzymatic property, that is, they hydrolyze ATP, right? They steal the high energy phosphate bond to go through their ratcheting. So myosin as an ATPase has, like any enzyme, kinetics, that is, how fast does it do that? Slow oxidative fibers tend to have myosins that are slightly different and have the slow ability to grab ATP, hydrolyze it, grab another one, hydrolyze it. And so they go through their ratcheting more slowly, thus they don't twitch as fast. Fast glycolytic fibers tend to have very fast myosin ATPase activity. If you want to think about it, there's again the nucleotide binding site, and so on. If you want to think about it in terms of enzyme kinetics, you could, if you're a biochem nerd, you can think about it this way. Just like any kind of substrate, you have substrate concentration, reaction velocity, and for different allozymes of any enzyme, you can have different kinetics. Some of them will have a high affinity enzyme will produce very fast reactions with very small substrate concentrations versus a low affinity that is a slow myosin ATPase activity would have a enzyme kinetic curve much more like this, would take a lot more substrate to get the same kind of velocity. That's what we're talking about here. There's an actual data, I guess, of steady state ATPase activity interacting with actin. But anyway, you get the idea. As you might expect, fast glycolytic fibers, largely anaerobic, largely deriving their ATP from glycolysis, are going to have the fewest mitochondria, whereas low, slow oxidative are going to have piles and piles of mitochondria. Now, keep in mind that the more mitochondria, this is an organelle, it has considerable volume to it. The more organelles you have, that means less space for actual contractile proteins. So this comes at a cost. If you don't have a lot of mitochondria, that means you can pack more myofibrils in there, which means you can produce more force. But on the other hand, you're going to be committed to just glycolysis because you don't have enough. Every cell is going to have some mitochondria. That's not devoid, but a lot more in slow oxidative. So anaerobic metabolism versus aerobic. Most fibers can swing both ways. And again, the number of cells that just do this versus just do this are very few compared to the number that are mostly somewhere here on the continuum. A word about ATP and its use here for just a moment. We have, aerobic oxidative phosphorylation down here versus glycolysis here. When we're making ATP, you only have about 5 seconds worth of ATP in any given muscle cell. So, in the time that it takes me to lift the coffee cup and bring it up here, I've exhausted all the ATP the muscle might have just lying around. Spare change, if you will. So muscles pretty much always have to be engaged in oxidative phosphorylation. I mean, even when you're sleeping, you're going to twitch, you're going to go into doggy dream mode, and you're going to be, going through your dream, and you're going to be using up the existing ATP in your muscle cells in no time, 5 seconds worth. So you're always going to be undergoing oxidative phosphorylation, always going to be engaged in glycolysis. On those rare instances where you suddenly burst into activity and you are and suddenly have used up all of your ATP, going from a dead stop, fire alarm, and you've been passed out, and suddenly you're recruiting your quads at this extreme rate. Well, in those weird situations where your muscles have really kind of spooled down, not doing a lot of anything metabolically, and then are suddenly called into extreme activity, there might be a gap during your ability in the time to produce ATP by either of these methods. And what are the muscles to do at that point? Well, we have this backup, the emergency change jar right here, in the form of creatine phosphate. And creatine phosphate is, which is CP here, is held inside the cells. It has in creatine, it's just creatine with a high energy phosphate bond and inorganic phosphate. And ADP that's lying around can steal that high energy phosphate bond and return to being ATP by stealing it from creatine phosphate. And you'll carry a certain amount of that spare change just around in your muscle cells that they can call on in these weird situations when they haven't been able to spool up fast enough. How important is this? Well, if you look to the world of capitalism and were to guess how important this might be, you would think it, well, and here's the actual creatine phosphate. Not that I care, there it is. You don't need to know that, but there it is. If you were to look to the capitalism world and ask the question, well, how important is it? They would tell you, oh God, it's really important. Here is creatine blast for clinically proven results. Recent clinical study at creatine blast conducted by Doctor of Medicine, Professor R.D. Sefula of the prestigious Moscow Research Institute and Practice Center of Sports Medicine. I give it to you that they know how to mess around with metabolisms. If you want performance, the Russians have been pretty good at it. They've validated creatine blast. Cell trans. Don't eat anything that says cell trans, ever. Formula to have significant performance enhancing benefits for advanced athletes and active individuals. I'm not sure if that's an exclusive group or not. The results of the creatine blast study conclude that the group using creatine blast experienced incredible gains. So I urge you to look up the definition of incredible. Lacks credibility, not credible. In strength, speed, and training intensity, 1,800% greater. Okay, 1,800%. Okay, so my bench press is 150, and suddenly I'm doing I'm doing a 3,000 pound bench. I'm an Avenger. I've got a shot with Black Widow. I mean, this is Captain Marvel, or Thor, depending on your preference. 1,800%. Well, greater than the control group. For all we know, that was a bunch of 80-year-old nuns. So does it do anything? I don't know. When you're gonna, this stuff is not cheap, by the way. You're putting a spoonful of it in your morning beer or whatever, and when you're paying $5 a spoonful, and then you go to work out, the psychology is, well, it's kind of like that of an aphrodisiac, I suspect. If you think it's going to work, it probably will. And I'm going to have a great workout. I have creatine blast coursing through my veins. Turns out what's going to really happen is that next time you're at the urinal, you're just going to be peeing away a bunch of creatine. Does that harm you? No. It's expensive. It's like taking too many vitamins. It's just, there they go. I feel better for just watching them leave me. It's stupid. Myoglobin. Oxygen binding protein that is binding oxygen inside cells. Obviously, if you're a fiber that does slow oxidative oxidative phosphorylation, you're going to need lots of myoglobin to hold oxygen as a little scuba tank, so you have plenty of oxygen as a terminal electron receptor in your electron transport, versus very little myoglobin in fast glycolytic fibers. This is what gives muscle fibers their color. What color thing they do have, red meat versus white meat, is given to them by myoglobin. So you're looking at turkey legs over here lots of myoglobin, turkeys can run pretty much forever. They have lots of myoglobin. They're very aerobic in their hind limbs. So their leg muscles are going to be at this end of the continuum, not way all the way over here, but at this end of the continuum. Their pectoral muscles, their breast muscles, turkey breast, as flyers, those are the muscles that produce the power for flight, they are burst performers, sprinters only. And as sprinters in flight, they're spectacular. If you've never seen a turkey fly, do. We got a billion of them here in town. Come up here to 29th Street or somewhere around Witham Hill, find some turkeys and scare them into flight. The neighbors that live there will thank you for it. They're spectacular to watch fly. It'll scare the crap out of you. You get close to them. It's a big animal, and they are tremendous flyers because their pectoral muscles are full of these incredibly powerful, fast glycolytic fibers that can pull them into the air. This is a big, heavy animal. They can fly as well as robins. They're truly amazing. The sheer size of these muscle fibers is different depending on the fiber type. Slow oxidative fibers tend to be small. Fast glycolytic fibers tend to be very large. The reason for that, let me just go to, new slide here, is simple. If you have a small fiber here, so here's a slow oxidative fiber, and by contrast, a white fiber that is a fast glycolytic fiber might be that large. If you are needing to move fuel into the cell and oxygen into this cell, again, those are processes that are dictated by, especially oxygen, Fick's law of diffusion. And so if you're diffusing oxygen into a small cell, the distances here are fairly small. And so it's easy to fuse oxygen into these little cells. These big cells, though, yeah, you can get oxygen to the perimeter of this thing, but it's gonna, for those myofibrils in the middle of this thing, it's gonna take a long time to get oxygen in there. And conversely, it's gonna take a long time to get the CO2 out. And so large fibers are limited in the rate that they can diffuse things in and out of the cell. So especially for oxygen and CO2, might want to, if you don't need oxygen immediately at a higher rate, you've committed yourself to anaerobic metabolism, then fine, I can be large. I'll make myself large. I won't have to worry about about even existing. I won't have to worry about diffusing in and out, and I can be as big as a cell can be. The little slow oxidative fibers, on the other hand, I need to diffuse at a high rate. Now you might ask then, okay, well then what's the advantage of being large? Why not? I understand that, but why would you sacrifice that ability just to be big? And the answer is simple. Again, here's the whole muscle. Let's say that's the whole muscle. And I'm just going to forget about fascicles. I'm just going to add muscle cells here. And imagine you have I'll divide it into two. And in this half, you have a muscle that's made of lots and lots of slow oxidative fibers. And when you have lots and lots of slow oxidative fibers, you're going to have all of the endomysium around them and all the connective tissue, the sarcolemma, and they're all of the connecting proteins like dystrophin, yada, yada, yada. All of that around every one of these cells. And so let's just say that all of that stuff is contained in the little red lines that I'm drawing themselves. Notice that a lot of that space is being taken up with those little red lines. That is, the little red lines are places where there are no contractile protein to produce any useful force. Contrast that with this half of the muscle where I have filled it with 2 giant muscle cells. Whereas almost all of the area here can be contractile protein. That's obviously, there are no muscles with 2 giant muscle cells, but you get the idea that when you make your muscle of lots or fewer numbers of large muscle cells, as opposed to lots and lots of little ones, you get more contractile protein bang for your buck. So a muscle composed of all fast glycolytic fibers is going to be inherently more forceful because more contractile proteins than one that is composed of lots and lots and lots of slow oxidative fibers. Sorry, keep forgetting that I have to clear that. There we go. Size is small, large. Let's see. And so finally, endurance of these things. Slow oxidative fibers, what you get is high endurance. They can be on in perpetuity. You have muscles right now that are on in your back. They're on all the time. They are contracting a little bit. They never fatigue. Versus you have muscles, white fibers in your gastrocs, for example, and in your quadriceps muscles, biceps, that would fatigue very quickly. That is, they go anaerobic. You will feel the lactic acid in those build up quickly because they're just using glycolysis. In the turkey, they don't fly far. They're strong flyers, but the farthest they're going to fly is to somebody's roof or up into a tree to get away. And then they're pooped. Their pectoral muscles are feeling the burn. Stretch. So we're all talking about input force here and the amount of force that a muscle produces that is the input end. That is how much the muscle fiber, if you were just to disembody it, how much force would it produce? So we can recruit more muscle fibers. We can recruit white fibers versus slow fibers, or slow fibers versus white fibers, depending on what we want to do. All of those things will determine how much force a muscle produces. But it also is important that the muscle is geometrically and physically prepared to contract. And this idea of stretch, how much a muscle is stretched before it starts contracting, is something that you may intuitively understand. If you've ever watched baseball or thrown anything, you understand that the windup is important. And since we're almost done, this is let me read to you from one of the greatest books ever written, Huckleberry Finn. This is my grandfather's copy. It's over 100 years old, and it's getting a little delicate. But how many have read Huckleberry Finn? Anybody? Nobody requires that anymore? Well, now is the time. Huckleberry Finn, of course, has run away from home, and he's with his black friend Jim, who is technically his slave, but that's not their relationship. And Huckleberry Finn's trying to figure out how the news of their running away is playing in society. And they're floating down the Mississippi River. And at one point he needs to figure out what's going on at home. So he needs to disguise himself and get the scuttlebutt. So he dresses up as a girl and visits, I can't remember this woman's name. It doesn't matter. Visits this woman's house and dressed as a girl and is trying to just kind of figure out what's going on. And this woman recognizes him as not a girl right away. She's been quizzing him. Well, I reckon you have lived in the country. I thought maybe you were trying to hocus me again. What's your real name now? George Peters, Mom. Well, try to remember it, George. Don't forget and tell me it's Alexander before you go. And then get out by saying it's George Alexander when I catch you. And don't go about women in that old calico dress. You do a girl tolerable poor, but you might fool men, maybe. Bless you, child, when you set out to thread a needle, don't hold the needle still and fetch the needle up to it. Hold the needle still and poke the thread at it. That's the way a woman most always does, but a man does it the other way. And this is the point, when you throw at a rat or anything, hit yourself up a tiptoe and fetch your hand up over your head as awkward as you can and miss your rat by about 6 or 7 foot. Throw stiff-armed from the shoulder, like there was a pivot there for it to turn on, like a girl. I await your angry emails. Not from the wrist and elbow with your arm out to one side like a boy. And mind you, when a girl tries to catch anything in her lap, she throws her knees apart. She don't clap them together the way you did when you catch the lump of lead. She'd give him a lump of lead to throw at a rat that was running around the house. When you catch, why, I spotted you for a boy when you was threading the needle. I contrived the other things just to make certain. Now, I'll stipulate that most of the women in this class can throw better than I can. The stereotype there is a bad throw. That is, it's throwing without stretching the muscle, standing up on your tiptoe and just kind of throwing like that without winding up. If you're never taught to throw properly or paid attention, as the girls in the 19th century were, you wouldn't understand that you need to stretch skeletal muscle to a proper length before actually starting the contraction of purpose. And so we'll talk a little more about pre-stretching and why that's important on Thursday and finish up skeletal muscle dynamics then. If anybody has any questions, I'll be here. Yeah, To Kill a Mockingbird's really good too.
Yeah, sure. I have 2 quick questions.
Yeah.
So the first one is on that one diagram where you showed us where there was those